Greetings everyone, Professor Simon here, ready to talk more about functions. So we left off in functions last time talking about basically what they are and how to find some of the important features. I wanted to hit again how to find the domain of a function once we have the function equation for it, and then I have some other topics that expand from there for us. Okay, so right here I've got several functions written in equation form for you, and we're going to just talk about the domain for each one, the domain on each one. Okay, so remember with domain, what we're looking for right now, until you hit something else later that adds to this list, but for now with domain, one, you're looking for division by zero, and two, you're looking for square root of negatives. Okay? So right now, that's all you really need to worry about. At your beginning stages of functions, there's only a couple of little pitfalls that can come down on the different functions that you see. The only other thing that we'll add to this list for this particular series of college algebra is we have to look out for logarithm difficulties with zeros and negatives and things like that. Okay? For now, let's just look at these two lists. If I'm looking at a function, like let's say f of x right here, right? Go down the list. Is there a possible division by zero? Well, there's not even a division in there, right, for one. But even if there were fractions, it'd be okay to have numbers in the denominator. The only time division by zero is going to come around is when you have variables in a denominator. All right, square root of negatives, there's no square roots. And let me clarify a little bit more. Square root is sort of a catch-all that we end up using a lot. Think more generically. It's actually any even-powered root that would have this difficulty. Okay? A square root is just the one that we see the most, but a fourth root, a sixth root, they would all have that same difficulty. Okay? So, for this first one here, you need to notice that I don't have any problems with anything. I could pick any number and I would be okay with raising it to a fifth power, to a 2 power. I would be okay with multiplying it by 7 or adding 4. All of those things have no exceptions. So this guy's domain is negative infinity to infinity, right? Okay, so A and G. These two functions are both rational functions. They have variables in a denominator. So we need to make sure and catch that right away for the number one. Are there numbers in this denominator that I could plug into this denominator that would cause a division by zero? And so you need to notice that because of this piece right here, x can't be negative 2. Because negative 2 plus 2 would be 0 in the denominator. Okay? Doesn't matter what the numerator has. I'm really focused on this one particular exception. So for A, my domain would be negative infinity to negative 2, union negative 2 to infinity. And the way you can think of this is I have everything to the left of negative 2, that's a whole interval, and everything to the right of negative 2, that's a whole interval. And they sort of just get cut at negative 2, and both of them have parentheses. So negative 2 is not included, right? So that's what you would call a cut in your domain. I've taken just the number negative 2 out, and that's it. Okay? Now, right here, g of x is equal to 19 minus x squared over x squared plus 3x minus 28. Again, I'm not that concerned with the numerator because there's no exceptions up there. But the denominator right here is something that I could plug a couple of numbers in and possibly get some zeros in the denominator. So I'm going to start by factoring this just because it makes it easier. And by the way, if you can't factor it, it's okay. You can still set it equal to 0 and possibly solve it. Well, since it's a quadratic, definitely solve it, right? Whatever's in the denominator, set it equal to 0 and solve, okay? I'm going to get away with it here with the factoring because it is easily factorable. Okay, but anything in the denominator, you're going to set it equal to 0 and look out for whatever solutions you get to that question. Those are the things you have to cut out of the domain of G. Okay, so then here I've got x squared plus 3x minus 28. That factors into x plus 7 times x minus 4. Well, this is telling me right here that x can't be negative 7. And this piece is telling me that x can't be 4. So I actually need to make 2 cuts out of the domain of G here. So I'll just start by counting from the left. I'm going to start at negative infinity. And then which one would I hit first, negative 7 or 4, if I were going along the number line? I would hit negative 7. I'm going to cut that one out, so I'll put a union and start up again at negative 7. And then keep going. Which one would I hit next? I would hit 4 next. Union, start up at 4 again after the cut, and keep going to the end of the number line. So then I have my domain there in interval notation. Okay, so we're going to switch gears again here. I've got h of x is equal to 3x minus 7 under a square root. Okay, and you know what, just to emphasize what I said earlier, I'm going to change this one too to a 4th root. Okay, so anything under a square root means I don't want the thing that the square root is acting on to be a negative. So what that implies is anytime you have something with an even powered radical, especially square roots, I'm going to take whatever's inside and I'm going to set that, whatever it is, I'm going to set it greater than or equal to 0. Then the only thing you have left to do is solve that inequality. The inequality will produce its own intervals to use as a domain. This is just a linear inequality, so I'll add the 7 and divide by 3. So that's one representation of the domain. X has to be greater than or equal to 7 over 3. But let's put it in interval notation, right? My domain is going to be starting at 7/3 and ending at infinity. Notice the bracket on the 7/3 because of the equal sign. Okay? So anytime you have some sort of radical that needs a restriction with negatives, the way you mathematically say that is, I cannot be negative, therefore I must be 0 or greater. And that's what greater than or equal to 0 is. So remember that. If I'm doing a domain on a radical, always put the greater than or equal to 0 on the thing inside. Okay? Notice this is the same thing. I have an even powered radical, so the inside has to be restricted to non-negative. So I'm just going to take that inside piece, 3x plus 4 divided by 5x minus 10, and that needs to be greater than or equal to 0. Okay? Now wait, don't make this mistake. Don't just say, oh, I'm going to multiply both sides by 5x minus 10. No, don't do that. Remember, we've done nonlinear inequalities here. We know that there's a different way that you have to approach this inequality. There was the step-by-step process, okay? And if you skipped over that video, or if you need to go back and refresh, go back to nonlinear inequalities, okay? That's where this is coming in. I have that step-by-step process where I get my little markers on the number line from each individual piece. You'll notice that the marker that I would get from this one would be negative 4/3, because if I were solving it, I would subtract the 4 and divide the 3. So negative 4/3 and then the marker that I would get from this one would be 2. Okay? Also, side note, x cannot equal to because that would cause a division by 0. But it's okay for x to equal to negative 4/3 because 0 in a numerator is okay. All right, so then I've got my little sections. And I'm just going to test each one. Let's plug in, x equals negative 10, for example. So if I plug in negative 10 here, I'll have negative 30 plus 4, which is negative 26, and negative 50 minus 10, which is negative 60, greater than or equal to 0. Double negative, right? These are both positives now. So a positive number bigger than 0, that's true. Okay? So my domain, I've already got a start on it. This section right here is negative infinity all the way up to negative 4/3. And we said it was okay to have the negative 4/3. Next section, I'll test 0 because 0 is in between those two. So if I plug in 0, I'll have 4 over negative 10 is greater than or equal to 0. And that's false because it's a negative number, which is not greater than 0. Okay, last section. Let's test x equals 10. So 30 plus 4 is 34. And 50 minus 10 is 40 is greater than or equal to 0. Yeah, that's absolutely true because it's positive, right? So this is true. Okay, so now I'll put a union because I see that there's another section here. I'm going to use just the trues as my answers here. That starts at 2 and goes to infinity. But remember, I have to put a parentheses on the 2 because 2 cannot be plugged into that denominator. It would cause a division by 0. Okay? So regardless of whatever else is in there, the process to finding these domains is for denominators, set them equal to 0 and solve, right? Whatever way makes the most sense. And whatever solutions you get, you have to individually cut. If it's some sort of even-powered radical, you take the inside, set it greater than or equal to 0. Greater than or equal to 0. And solve that inequality. Okay? Those are your most common domain techniques. Something else I wanted to hit again and expand on was the function notation that we use to talk about function equations. All right, we got the basics last time by talking about when we plug numbers into x and things like that. But let's go through the whole process again and expand it for y's as well. Okay? Because remember, functions are supposed to be input-output machines. You give them a number, they give back another number. Most of the time, you should expect that the number you're feeding them is the letter that's in the parentheses. However, we're not always limited to those kinds of questions, okay? So you need to pay attention to the way the things are written and the location of the value that's being asked about, right? So right here, f of 4 equals. Don't forget that this means x equals 4, and I don't know what y is. Okay? Well, straightforward. F of 4, I plug the 4 into x. So 5 plus 4 over 3 minus 4. F of 4 would then be 9 over negative 1, which is negative 9. So f of 4 is negative 9. Okay? F of x equals 3. Let me move that one, give myself a little bit more space there. F of x equals 3. Now, notice that the 3 is not in the parentheses, okay? It's important to notice that the 3 is actually where a y would be, because y is equal to the function. Y is the output. So this is telling me I don't know what x is, but I do know that y is 3. Okay, so it's the opposite than the other one. You can still work this though. I take my function, and since f of x equals 3, then f of x, I replace it with the 3 right here. So I end up with an equation instead of an expression that I can simplify. This just becomes an equation that I need to solve, right? Okay, so it's a rational equation. We've talked about those, right? I'm going to multiply both sides by 3 minus x. So then from here, I've got 9 minus 3x is equal to 5 plus x. I'm going to subtract x from both sides. Right? Okay. Let me go ahead and separate this. And I'm also going to subtract 9. So that gets rid of this, and it gets rid of this. So I've got negative 4x is equal to negative 4. Dividing both sides by negative 4 gives me that x is 1. What does this tell me? It tells me that f of 1 is 3. Right? Because that's what they gave us earlier. They gave us the y value and not the x. I found the x that works. And by the way, whenever you plug in an x, you will only get one y. That's the definition of a function. But vice versa, if you give me a y, you can actually have more than one answer to this question, because it's okay for just normal functions to split off in the reverse direction. On that same note, we can talk about in general the definitions that we gave intercepts, right? A y-intercept is a point where a graph hits a y-axis. But on the algebra side, by definition, a y-intercept is whenever x is 0. So for functions, that would be plugging 0 in for x. In the case of our function here, that would give me 5 plus 0 over 3 minus 0. So f of 0 would be 5/3. This would be the point 0 comma 5/3 would be where this particular graph has hit the y-axis. Vice versa, an x-intercept is whenever y is equal to 0. So in the same token, if I say f of x equals 0, that's like saying my y is 0, what's my x, right? Ask the question. Well, let's solve it. That means 0, right, is equal to 5 plus x over 3 minus x. I'm going to solve it the same way I did before. I'm going to multiply both sides by 3 minus x so that this goes away. But anything times 0 is just still 0, right? So I have 0 equals 5 plus x. If I subtract 5 from both sides, then what I get is negative 5 equals x. So what this is telling me is that f of negative 5 is 0. Okay? So when you're looking on not just lines and not just those few shapes that we've talked about there, okay? When you're looking in general, all right, these things have functional definitions. Y-intercept, x is 0, plug in x for 0, plug in 0 for x. X-intercept, y is 0, so set your function equal to 0. Okay? We use those as generic definitions for intercepts. Okay, now something else that didn't come up last time is a special kind of function, a piecewise function. And really what this is a human function. Okay? A piecewise function means that someone came across some sort of pattern or some sort of calculation that requires a decision, and not just one function from mathematics can give all of the answers that this particular person needs. Okay? So I call them decision functions, all right? Remember, if you feed one x in, you should only get one y out. That's the definition of a function, okay? This just gives you an extra step in the process of calculating, in that you get to choose. Do not plug the x value into all of them. You have to choose one. This particular one has 3 pieces. There's no limit. A piecewise function can be 100 pieces if it wanted to be. A lot of the ones we run into are either 2 or 3 pieces. Okay? For this one, it tells me over here, this is how you make your decision. Okay? My decision is made off of whatever I feed in, not what I calculate. Whatever number is coming in, see x, that's the number that will be used in the calculation, but don't do it yet. As soon as you feed the number in, you make your decision. Hey, is that one less than 0? Hey, is that thing you fed me in between 0 and 2? Or, you know what? Is that number you fed me between 2 and 10? You need to make that decision first. Then, once you said, oh, look, it's this one, then you just pick the one calculation. Then you plug it in, do the calculation, get your one answer from that. Okay? So, in this one right here, let's go with the first one. P of -2. Right? Don't just start plugging -2 in. Take -2 over to the decision column. Is -2 less than 0? Is -2 between 0 and 2? Hey, wait a minute. -2 is less than 0. So this is the one that I pick. -2 squared plus 5 is 4 plus 5, which is 9. All right. How about P of 25? Well, okay, so take the 25, make a decision, right? Is 25 less than 0? Is 25 between 0 and 2? Or is 25 between 2 and 10? None of those, right? 25 is bigger than 10. It's greater than 10. So it's not in any of the lists. That means this function can't use 25. It's not in the domain of this function. So I put undefined. Don't put no solution, because we're not solving. It means that the function is not defined at that x value. At that location, no function value. Next, P of 1. Is 1 less than 0? Mm-mm. Is 1 in between 0 and 2? Yes. So, where do I plug 1 in? There's no x, it's just 9. Okay, well, easy. No calculation necessary. It's telling you if you fall into this category, give it a 9, period. So P of 1 is 9. All right, P of 2. Well, okay, is 2 less than 0? Is 2 in between 0 and 2? Well, wait a minute. Maybe, because it's on the endpoint, right? Oh, but there's no equal sign. Can't use it on that one. P of 2. Is 2 greater than or equal to 2? Yes. Because the equals is here on the 2, P of 2 will fall into this third category. And I'll just do 4 minus whatever the number is, in this case, 2. 4 minus 2 gives me 2. Okay? Now, in general, when you're finding the domain on one of these things, right? The domain is even easier than some of the other functions, because you just need to look for your little exceptions, and of course a lot of these don't have that. But in general, these things are going to be defined on regions where they're already capable. Okay? So really, if I just take all 3 of these together, that gives me my total domain of the entire function. Right? So in this case, less than 0. Well, that's negative infinity to 0. Union with 0 to 2, union with 2 to 10. And anytime you have the same number and one of them's bracketed like that over a union, you can actually Lego them together, right? They'll actually lock together. If it's two parentheses, no go. But as long as one of them has the included, you can actually merge them together on that same number like that. So look, it jumps and merges here. Same thing, there's a bracket that merges again. So it's going to go just from negative infinity to 10. And that's my domain here. Okay? So, another question. I know we did both sides on these things. How do I plug in a function value? And then how do I find a value that needs to be plugged in? You can do the same thing with piecewise functions. With a piecewise function, what if I were to ask a question like, where is p of x equal to 1? Okay? Where is p of x equal to 1? Or let's make it an important question. A lot of times people ask about intercepts, right? Where is p of x equal to 0? That would be like finding the x-intercepts, right? This is a valid question. I have a function equal to a y value, okay? So, it's a reverse of a decision, okay? Instead of you making the decision by plugging in a number and by seeing which one it fits, you have to reverse it. I have to actually put the equals 0 on all of these and then reverse in see if the x values I'm getting are in the decision regions. Okay? So look, if p of x equals 0, let's say, I need to solve 3 equations. In this case, I'll need to solve 0 equals x squared plus 5. I'll need to solve 0 equals 9. And I'll need to solve 0 equals 4 minus x. Okay? But be careful. When I solve these, I still have to check and make a decision afterwards. Because remember, once I have an x value, I can make a decision. Okay? So I solve this. I subtract 5. I square root both sides. I'm going to get plus or minus square root of 5i because of the square root of the negative. Well, we're not dealing in any imaginary numbers, so this isn't going to give me anything. Next, 0 equals 9, that's false. So that's not going to give me anything either. Over here, 0 equals 4 minus x. If I add x to both sides, I get x equals 4. Okay? Now, I'm not done. Where did the 4 minus x come from? Right here. This is his decision. I now have an x to check. Is 4 in between 2 and 10? Yeah, it is. Well, then this is it right here. This is one of the answers that I could have gotten. P of 4 is equal to 0. I could have gotten more than one answer here, by the way. Each one of these could have given multiple answers, right? This one tried to give 2 answers. We're just not doing imaginary numbers. Here, this one had no hope. Unless you put equal to 9, you're never going to hit that one. But okay, so with piecewise functions, the decision has to be made at some point. But decisions can only be made with x values. So if you're given an x value, you can make a decision. If you have to find an x value, well, then you got to find them first and then see, does that x value make the decision for this piece or decide to be in this piece, okay? Just like we like to study the rate of change on lines when we were talking about slope, we generalize that same idea to all functions, really. But we call it the average rate of change because any other function besides a line, they're not straight and they don't keep the same slope at every point. So it's an average rate if I can pick a beginning and an ending point and you're just basically smoothing it out to a line just between those 2 points. Okay? So this is what it is. You're really still doing just a plain old slope calculation. Okay? The difference is I'm not going to be given the y values all of the time. What I'll be given is a function and some x values, a beginning and an ending x value, okay? So you'll notice it's really the same formula, because when I plug an x value into a function, it gives me back a y value. So this is really saying y2 minus y1 still. So it's still rise over run. It's still a slope. It's exactly the same. The difference, like I said, is that the function itself is going to be curved in some sort of way, and you're trying to just take the slope of some line connecting those 2 points. Okay? So for a brief moment, you're just straightening your ideas, and you're taking an average speed, an average rate of change between the two, right? So let's get an example in here. I have this function 4x minus x cubed, right? There's a very rough graph of it there. So, and then I want to calculate the average rate of change on 2 different intervals so that you can see that it is in fact it constantly changing. Okay, so first we're going to calculate the average rate of change on the interval from -1 to 1. Okay, so those are x numbers, right? The interval from -1 to 1 in x numbers. Here's -1 on the x. Here's +1 on the x. Okay, so -1 gives me something really close to the bottom right here, and +1 gives me something really close to the top right here. And basically I'm just finding the slope of the line that connects those 2 points. And it won't necessarily be the same as the function itself, because the function is curved a little bit along that way. And I'm just finding the slope of the line that connects those 2. Okay, so let's do that. First thing I need to do is find the 2 function values that go along with that, because I need my y values. So I'm going to have f of -1, that's f of x1. Okay, so I plug that in. 4 times -1 minus -1 cubed. That's going to give me -4 plus 1, which is -3. And then f of 1 is going to be 4 times 1 minus 1 cubed, which is just 4 minus 1, right? That's 3. Okay, so remember, these are y values, right? So my average rate of change is going to be y2, the 3, minus y1, the -3, divided by x2. Now remember, which x went with this y, okay? This 1 right here went with it. So 1, and then x1, right? With the -3 went -1, minus -1. So all I'm saying is you got to be a little careful here when you're doing these. You actually could reverse them, you know, by accident or whatever, as long as you keep them together, right? This y went with this x, this y went with this x, and it'll be all right. So on the top I'm getting 6, on the bottom I'm getting 2. So my average rate of change here is 3, right? A +3 slope, positive. Notice the direction of the line from left to right is a positive slope line. Okay, let's do it again for a different interval. The interval where x equals 1 to x equals 3. All right, well, x equals 1 is here, right? We already did that. That's this point right here. And x equals 3 is actually really far out of reach off of the graph. So we're talking about a line that's going to have a really steep slope here, going like this, until it hits the graph way somewhere far down here. Okay? So I'm getting a line going in this direction. So I'm actually expecting a negative slope this time, right? Between 1 and 3 on the x-axis there gives a huge drop in my y value. Okay, so f of 1 we already know. right? We calculated that a minute ago. F of 3, 4 times 3 minus 3 cubed. That's going to be 12 minus 27, right? Negative 15. Huge negative number compared to the scale that I have on my grid there. Okay, so now average rate of change. Is equal to negative 15 minus 3 divided by 3 minus 1. The intervals don't always have to be a gap of 2, by the way. It just so happened that these two intervals I picked both had a gap of 2. I'm getting negative 18 over 2, which is a negative 9 slope. That's actually a very large negative slope. You can tell too, right? It's a huge drop. But my point is made. At one part of one function, it's a positive slope. And then another section of the exact same function is a negative slope. Okay? That's why we calculate the average rate of change the way we do, because it changes. So I may be interested in a larger interval sometimes. I might be interested in a smaller interval sometimes. It just depends on how I want to approach my function and where I think some of the curves may be, or just what it means to my application. But average rate of change is just slope. Okay? Keep that in mind. Same formula. Looks fancier like this, but same. Okay?
So I just wanted to give you a better view of that graph we just talked about with the average rate of change. It was f of x equals 4x minus x cubed. Here's a really good graph of that shape. Much better than I could do by hand. And I can stretch it out a little bit so we can see the important parts a little bit better here. So of course it looks this way, but you know the scales are not equal anymore. So I've stretched out the x to the important parts that we were looking for on that first part. In that first part we were going between these 2 points. At negative 1 it was at negative 3, and at 1 it was at positive 3. And I have the segment here, of course. This is what we're actually calculating the slope of, the line that connects those 2 points. And as you can see, the slope is indeed 3, as it has calculated there. The other segment that we did, you see I have the point already set up, 3 and negative 15, but it doesn't fit too well on the grid, so I'm going to have to change the y interval here to make it fit just a little bit. Here we go. There it is right there. So I'll move this up a little bit. Okay. So these are the other 2 points that we did on the interval from 1 to 3. So of course at 1 it's at y value of 3, and at 3, just as we calculated before, it's at negative 15. And so we are finding the slope of this segment here. The average rate of change is the slope of this line, which, as you can see, is a negative 9 as we calculated.
Last thing I want to talk about in this lecture is difference quotient. And I want to give you 4 examples. So I'll have these 2 and then 2 more right after. Difference quotient is another attempt to measure a slope on something that is not normally just a straight line. Although you can do this to a line, and I'm going to start there. Okay, but the idea is still slope. And you can see it looks somewhat different than the average rate of change that we were just talking about. But the overall structure is still there. You can see the fraction bar, and then this is a rise and this is a run. But now the run has been redefined so that it's a single value. And really the idea there is that I can control the run kind of like a slider bar, right? I can let it be as large as I want or as small as I want, and it's controlled by this one variable here, h. So you can see h is actually the length of the run. And what's happening is, just like in the average rate of change, I'm taking these two x values, the beginning x that I start with, and whatever the next x is after I add h to it, x plus h. So I'm taking those two x values and plugging them into the function, just like we did with average rate of change. And once I plug them in, these are two y values. And then the subtraction of those gives me the rise. Okay? The real difference with difference quotient, though, comes in the fact that we don't actually pick intervals. What it is we just find the difference quotient of a function generically. So it's sort of like the next step up. And this is actually also a half step towards the study of calculus. And don't let that scare you. That's actually a good thing. Okay? So we're going to do the difference quotient on some examples here. And what that means is we're going to be making generic formulas to be able to calculate slopes wherever and however large we would like. Okay? So first example, a linear function, negative 2x plus 5. When you're doing difference quotient, what you want to start with first is having all of the pieces. Okay? The first thing you need to realize is you've already got half of the numerator. Okay? The numerator has the original function in it, you see, f of x. So I've already got that piece. This is what I mean. For my difference quotient here, I already have something minus negative 2x plus 5. And then I already have the denominator too, it's always h. Okay? So you always start out this way with difference quotient. You always are given the function. There it is. It goes in that spot every time. And h is always down here. The trick is to get this part. Okay? The f of x plus h. In this case, I'm going to do g of x plus h. And remember, all that means is wherever you see an x, I'm directly replacing it with x plus h. I'm plugging that in. So here it is. That would be negative 2 times x plus h plus 5. Direct replacement. Instead of x, I plug in x plus h. Distribute my 2, and that's negative 2x minus 2h plus 5. G of x plus h is equal to this quantity. So this is what goes here. Negative 2x minus 2h plus 5. From here, you just keep simplifying until this h is gone. The h in the denominator is the goal here. I really don't want that there in case I have to let h be 0, because I don't want to have to divide by 0. Okay? So difference quotient is equal to, I have negative 2x minus 2h plus 5, distributing this negative here. Be careful when you're plugging that in, right? The original function, I put it in parentheses on purpose because that negative from the original formula needs to distribute. Plus 2x minus 5 all over h. At this point, no matter what in your difference quotient, you should see a lot of things wiping out to 0. Minus 2x plus 2x. Plus 5 minus 5. I'm left with negative 2h over h. And in this case, notice h over h is just 1, so I'm left with negative 2. Okay? Now, if you think about it, this should make a whole lot of sense. This is a linear equation, and that's mx plus b form. Remember, m is the slope. Difference quotient is a slope calculation. All this is telling me is that the slope is negative 2 everywhere for any h value, for any x value, for any size. The slope is always negative 2. And that's true. It's a line. The slope doesn't change. Okay? So the difference quotient is actually overkill for this function because we already knew the slope. I just wanted to get the process out and choreographed for you. Okay? Let's do it to something where it really matters. Something that is not a line right? Something that is not a line. It's actually a parabola. And we're going to find the difference quotient of this function here, okay? So that means we'd be able to find the slope anywhere we want. I'm going to start by writing down what a of x plus h is. Remember, we need that for the front part of my formula. All that means is I have some function, right? This is actually what your function looks like right here. This is truly like a function in waiting right here, okay? Notice I've written blanks instead of x's. We use letters to represent missing spots or taking place of generic spots, you know? But if you think about it, this is really what a function is. He's waiting for something to get put in to those parentheses. And in this case, what have I put in? X plus h is what I'm putting in. So that's, I plug that in here and here, right? Okay, so let me set up the difference quotient. Difference quotient is going to be this piece minus all of that at once. And I say that at once because I need you to realize why I'm putting this in parentheses. And then all of that divided by h. Right? From here, it's just simplifying now, like I said before, until I can get rid of this singular h here. So I'm going to start by multiplying this out. Now don't forget, I can't just square x and h. I have to actually write x plus h, and multiply it out. What that's going to give me is 6x squared plus 2xh plus h squared. Okay, here I'll just distribute my 11. Minus 2 is still minus 2. And here I'll distribute my negative. Okay. Now you may already notice some eliminations here, right? The minus 2 and the plus 2, and also the plus 11x and the minus 11x. Okay. Really, you got to realize the goal is the original function should always wipe out. Okay. And you'll see that that's going to happen right here, right? I'm going to have 6 times x squared and minus 6x squared. Those are going to go away. So that leaves me with, after distributing here, I've got a 12xh. I have a 6h squared. I still have a plus 11h right here. And that's it. Everything else zeroed out. And this is still divided by h. Well, in this case, I've got multiple pieces here. And it's some people like to factor and wipe it. To me, in this kind of case, what's easier to do is to just go ahead and distribute the denominator. I'm going to use the distributive property here. So watch. The pluses and so they can go here, and I can just distribute the h along this. But that's still distributive property because it's division over a list of additions like that. You do that in reverse all the time when you're adding things with common denominator. I'm just unadding things with common denominator now. And this allows me to simplify here. Notice my h's, right? H over h is 1, h over h is 1, and here one of the h's wipes out. So my difference quotient is 12x plus 6h plus 11. Okay? This is a slope calculation for that function. And the only two things that you need to give it is a location, an x value, and a size of an interval, like how big of a slope you wish to measure. And that would be the size of h, right? I just need to give it a beginning value and a width of the interval. I have to give it an x and an h, and I can calculate just by plugging in those two values. It'll give me the slope of this function over and over again. Okay, so you can see how this would be sort of the next level from average rate of change. It's calculating the exact same thing, but now I have a way to crank out several of them just by putting in a location and a size. As promised, I said I would have 4 examples for your difference quotient. Here's 2 more. These are less as often, but in case you ever run into some other kinds of functions that aren't necessarily polynomial, here's some other difference quotient, examples that can come up outside of that. So a rational function and a square root function. We'll see how we'll do the difference quotient on these. Same process as before. I start by finding the function if I plug in x plus h, right? That's how you always want to start these. So in this case, I'll have r of x plus h. And really, it's just right here, instead of x, I've got x plus h, right? I'm plugging in for x there, x plus h. Okay, so to set up my difference quotient, I'm going to have that one minus this one. So that's 10 over x plus h plus 2 minus 10 over x plus 2, and then all of that over h. I know, fractions, and more fractions, right? I need you to think back to some of your old school simplifying days and remember, how do I handle a compound fraction, a fraction with fractions in it quickly? And the answer is to multiply by the LCD in both the top and the bottom of the big fraction. I'm looking at my denominators. Technically, this h is over 1. The 1 is a denominator. X plus h plus 2, that's a denominator. And x plus 2, that's a denominator, okay? So what I'm going to do here is I'm going to multiply by the common of those. And these are too complicated to try and pick apart. So the common denominator is just multiplying them together, okay? So I'm going to multiply by x plus h plus 2 times x plus 2. X plus h plus 2 times x plus 2. And that means I have to multiply it here also. X plus h plus 2 times x plus 2. Okay? Now what does that do for me? Well, this is multiplication. This is division, right? That leaves me with this. This goes away with this. This goes away with this. And so it simplifies this numerator quite a bit. I have 10 times x plus 2 right here, minus 10 times x plus h plus 2. And then the denominator got a little bit worse, but not so much that I couldn't do something with it. Okay? And at this point, we're actually almost done. Watch. I'm going to distribute the 10 here, and I'm going to distribute the negative 10 here. So that gives me 10x plus 20 minus 10x minus 10h minus 20 all over h x plus h plus 2 x plus 2. Okay, so here's that point, like in the last one and the one before that, where things start eliminating. Look, I have plus 10x minus 10x. I have plus 20 minus 20. That leaves me with a negative 10h in the numerator. Okay, now I'm going to write this in shorthand. it's h times blah, blah, blah times blah, 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 okay? Because I'm not worried about what's in those right now. I'll copy it again in a minute. I needed you to focus here. Only negative 10h is left in the top, and the h in the bottom is multiplied right here, and so is this h here. You can actually reduce these because it's just h over h. It's just multiplication and division at that point. So my difference quotient can finally be negative 10 divided by x plus h plus 2 times x plus 2. And then I have, a generic way of calculating slopes for that function. All right, let's handle this radical function. Just like before, you want to start by plugging in x plus h. So b of x plus h is equal to the square root of 7 times x plus h plus 8. Like that. Okay, so and if it helps you out, you can go ahead and distribute that out. Square root of 7x, 7h plus 8, like that. Okay? So then my difference quotient. B of x plus h minus b of x all over h. Okay? Now, what we are left with to do is to get rid of these radicals. Right? We would like to be able to combine all of those and be able to get the things that I need out to reduce with this h. The only way to handle that is by doing the conjugate. Think back to your square root times, and when we were multiplying things, the conjugate means I take the same two objects, but instead of subtraction, I would switch it to addition. Okay? And what I'm going to do is I'm actually going to multiply that conjugate to the top and the bottom of this big fraction. So I'm going to multiply the conjugate here. That's square root 7x, 7h, 8, and plus, right? So, like that. And then, of course, whatever I do in the numerator, I have to do equally here. So square root 7x, 7h, 8, and plus square root of 7x plus 8, like that. Now here's where the fun part comes in. If I FOIL out this numerator, I have to multiply a square root times itself, right? And don't forget, when you're dealing with nothing but positives, a square root times itself just gives you what's inside. For example, square root of 2 times square root of 2 is just 2. Okay, so this square root times that one just gives me 7x plus 7h plus 8. That's it. The same thing goes, by the way, for this last one. I'm doing this one times that one. It's the same radical again. The only difference is it's a negative times a positive this time, so I would have minus 7x plus 8. Okay, now wait a minute, Professor Simon, you skipped over something there. That's not all the multiplications in FOIL. You're right. But I don't have to write anything else here. Here's why. When I multiply this first radical times the very last one, and this second one times this one here, both of those inner and outer terms are equal in size. Notice it's this radical times the other one. And then it's the same multiplication here as well. But the first one here is positive. The second one is negative. No matter how big or how messy those are, you're crisscrossing, and those two multiplications match every time, but one positive and one negative. They're going to add to 0 every time. That's the lovely part of conjugate. Anytime you multiply two conjugates, the inner and outer terms are going to wipe out. So I'm left with just the first times the first and the last times the last, giving me something much nicer in the numerator. Okay, now of course, the denominator got a little messier, but I don't need to simplify the denominator at all. It's not causing any problems right now. 7x, 7h, 8, and square root 7x plus 8, like that. Okay, if I distribute that negative, seven x, 7h plus 8, minus 7x minus 8. Okay, I'm going to blah, blah, blah it again, because again, I want you focusing somewhere else. So look, in the numerator, I distributed this negative, and that gives me that wipeout time, right? 7x minus 7x plus 8 minus 8. Okay? All right. Then again, all I'm left with in the numerator is 7h. That's the only thing left in that numerator. And I have h times this big chunk. Again, the chunk doesn't matter right now. What matters is I have times h here and times h here, and those are the only two terms, top and bottom, like that. So I have the h over h is going to give me 1 again. So my difference quotient is 7 over square root of 7x plus 7h plus 8 plus square root 7x plus 8. I know these two are a little bit more complicated than the other ones, but the end result is I can actually do, right? We can actually find formulas for these slopes of these functions, and that helps us study functions when we can study how they change. Okay? So I hope that the study of these functions here has helped you in your endeavor of studying algebra.